So in today's class, we looked at exponential functions with the base of e and started to look at how to determine the half-life in these models, meaning how long does it take for the decay to drop to 50% of what it started as. And we talked about how you can use just the inverse of the exponential with the base of e, which is the natural log. So we did like natural log 0.5 equals negative 0.04 t, and then we could divide by negative 0.04 on both sides. And we basically said that we could always do natural log of 0.5 divided by the k value would give us our half-life, right? So the question is, what if we have functions with non-e bases like 0.9, 0.8, and 0.7? So the first thing you should think about here is what kind of decay is this representing? In other words, what percentage are we losing each unit of time in each of these models? So we're losing 10%, right? We're losing 10%. We're losing 20%, and in this case, we're losing 30% as t increases by 1. So the question is, well, if I'm losing 10% every unit of time, then, or every year, we'll just say, how long is it going to take before I drop to 50%? All right. So we're losing 10% per year does not mean that we're going 90%, 80%, 70%, right? This is not what's happening. Because what happens is we're going to drop to 90% of what we started as, right? 90% of 100 is 90%. And then we're going to take 90% of that now. So 90% of 90% is going to be 81%. And then we're going to take 90% of that. So 90% of 81% is going to be 72.9%. So the question is, how many times do we have to drop by 10% before we hit 50%, right? So with each of our models, we can just set them equal to 0.5, right? This is saying, what is our t-value going to be that we need to plug in to make it 50%, all right? When we're dropping by 20%, how long until we hit 50%? When we're dropping by 30%, how long until we take 50%, right? So take a second to think about this. What are we going to do here? How are we going to solve for t? Well, we're just going to use a logarithm, right? Log, and our base is 0.9, and we're trying to figure out what power we have to raise 0.9 to get 0.5. That's what this log is going to tell us. Log 0.8 of 0.5 equals t, and log 0.7 of 0.5 equals t. What power do I have to raise these different bases to in order to get 0.5? That's what this logarithm is going to tell us. It's going to tell us that t value. Okay, so this is what we should be getting. Here's our different half-lives for our different scenarios. Now, you might be able to figure out if you have a more a newer calculator, right? You might be able to figure out how to do these logs using your calculator. You also might be able to figure out how to do it using Desmos. If you have a more basic calculator, it's easier to use the change of base formula. So we could say log of 0.5 divided by log of 0.9. Log of 0.5 divided by log of 0.8, and then log of 0.5 divided by log of 0.7. That's our change of base formula that will allow us to evaluate these different logs. Or if you can figure out how to plug in a log with a different base into your calculator or use Desmos, then that's fine too. Either way, you have to arrive at these answers. So if I drop by 10% every year, it's going to take 6.58 years to drop to 50%. If I drop by 20% per year, it's going to take 3.106 years to drop to 50%. If I drop by 30% every year, it's going to take me 1.94 years to drop to 50%, right? And we can do this for any amount of percentage as our base. If we want to figure out, if I drop by 32% every year, well, that would be 0.68 as our base. So we would just say log of 0.68 of 0.5 equals t, right? This is going to tell us if we lose 32% every year, how long until we hit 50%. That's what this t value will tell us. So then we can use those half-lives to come up with a k value to put this exponential model into a base of e. okay? So once I know the half-life, I can figure out, okay, so e to the kt equals 0.5, right? I now know what the t value is. I'm not going to write it in because it's this long decimal. But what I can do now is I can say k times t equals natural log of 0.5, and then I can divide by that half-life value that I just got, and that's going to give me my k value, right? And I can do this with all three of these t values. Natural log 0.5 divided by this, natural log 0.5 divided by this, natural log 0.5 divided by this. And what that's going to do is it's going to give me these different k values that I have in these models, right? So when I did natural log 0.5 divided by roughly 6.579, right? And you can just go ahead and type in that whole decimal as opposed to rounding, but I'm just going to write the rounded number here. That equals negative 0.10536 ... right? This long decimal here. So that's my k value, right? So then if I want to write my 0.9 to the t, if I want to write that as with an exponential constant base, then I can write e to this k value times t. So these two functions are equal just with different bases, right? 0.8 to the t, this is e to the negative 0.22314283229 t, right? These are the same function just with different bases. If you type in e raised to this value and just take out the t or make t 1, then you should be getting 0.8. If you type out e to this value, you should be getting 0.9. If you type out e to this value, you should be getting 0.7. Okay, so what we're going to get into eventually is that it's easier to do calculus on functions with a base of e. There's easier derivative rules for functions with a base of e as opposed to bases that are not e. So that's why it might be beneficial to convert our function to a base of e. So here's just another example. What is the half-life of an amount that decays 25% annually? So again, we're going to do log of 0.75, log base 0.75 of 0.5. Okay, what power do I have to raise my 75% base to in order to get 50%? And then we can just, again, use the change of base formula if needed, and we get that the half-life is 2.4094284. And then once we know the half-life, natural log of 0.5 divided by the half-life will give us k, which in this case is this negative 0.28768299724. So then if I have a function like 0.75 to the t, which this is going to model 25% decay every year, we can set that equal to e raised to the negative 0.28768299724 times t. So these two functions are equivalent, just with different bases. Okay, that's all I have for today.